Good morning to every one of you. Myself, M. Ramarao, Secretary, IGS Guntur Chapter. This is 29th webinar of IGS Guntur Chapter. This lecture is organized by IGS Student Chapter, Malineni Perumaldu Education Society's group of institutions, Guntur. And IGS Guntur Chapter, established in 2003, organized a number of seminars, workshops, significant being IGC 2009 National Conference at RVR and JC College of Engineering. I am thankful to Mr. Ravi Sundaram, Director, Sengras Geotechnical Private Limited, Noida, to deliver this lecture, Geotechnical Investigations in Difficult Ground Conditions, Field Experience. Before introducing the speaker, few announcements to participants. I request all the participants, please stop your video. And during the lecture, you are going to chat with the host only, that is myself. And you may chart audio and video issues. Please do not share your information and questions during the lecture. After completion of the lecture, I am going to share Google Form link to share the PDF content of this lecture and your feedback. Question answer session through chat at the end of the lecture. Our next webinar tomorrow at 11 AM, so that is Friday, by Engineer D.V. Bhavana Rao, former Chief Engineer, Roads and Buildings Department, Andhra Pradesh. And the title of the lecture is Construction and Quality Assurance in Rigid Pavement. So, Mr. Ravi Sundaram is founder director of Sengras Geotechnical Private Limited and directs the company's geotechnical consultancy services and geotechnical construction activities. His expertise includes geotechnical investigations, geophysical surveys, ground improvement, and groundwater studies. He has been involved in developing engineering solutions to problems of foundations under Artesian conditions, collapsible dune sands, soft clays, expansive soils, etc. His special interests include foundations for tall buildings, thermal and solar power plants, and bridge foundations, as well as the testing of pile foundations and strengthening weak, distressed foundations. He has published over 60 papers reflecting his experience in geotechnical practice. He strives to integrate field experience with academic research in order to respond to complex geotechnical challenges facing India. Received IGS Professor Dinesh Mohan Memorial Award 2017-18 for excellence in professional practice. Delivered the prestigious 6th Madhav Lecture in honor of Professor Madhav, former Vice President of Asia, ISSMG, in 2007 on geotechnical investigation in difficult soil conditions, Indian experiences. Received IGS Delhi Chapter Lifetime Achievement Award in 2001. Now I request Mr. Ravi Sundaram to start the lecture.
Thank you very much, Professor Ramarao, for that very kind introduction. Today I will be talking on geotechnical investigations in difficult ground conditions. The thrust here will be on the field experiences which I have had working on various projects in our country. This presentation is taken primarily from my 6th Madhav lecture, which was held in Hyderabad in honor of Professor Madhav, one of our greatest geotechnical engineers in India. Here I will be trying to cover all some of the difficult conditions. Of course, it is not possible to envisage all kinds of ground conditions which you could encounter. As you know, geotechnical investigation is a vital part of all geotechnical studies. It generates most important field and laboratory data for the foundation design. It's a prerequisite for economical and safe foundation design. Whatever is envisaged at the investigation stage and the has to translate into construction that is in sync with the design concepts, the assumptions made in the design, and predicted foundation behavior. The geotechnical investigation on all projects is the most critical part, and when the ground is tough and difficult, it becomes more challenging to be able to meet these requirements. Let's first understand what is a difficult ground. When we say difficult or a puzzle, it may be difficult for one person, but could be easily solved by another. So how many of you have solved this Rubik cube puzzle? The world record is 6 seconds. So the ground is the same. So it's all about knowledge and understanding. That means the knowledge of geology, information on performance of foundations in the vicinity, data on past failures, if any, understanding the engineering properties and behavior of the ground, modeling the soil structure interaction in the right way, and implementing the design concepts in construction. Obviously, the detailed geotechnical investigation has to clearly define the soil classification and the relevant engineering properties which are required for the design. So insufficient knowledge is what creates the problem. The limited data is another issue. So both these things could make your problem difficult. It increases the uncertainty in the design. The design assumptions have to be validated. That's very important, and you may not be able to do that. As a consequence, the design may be conservative, leading to a higher foundation cost. On the other hand, the safety of the structure could be compromised, and that could be a failure in the first case. So the solution is obviously to understand, improve, and acquire knowledge. Obtain relevant geotechnical data, evaluate the problem, perform additional tests if required, interpret data in a scientific manner, work out a solution that addresses the problem and resolves it. So this is a geotechnical investigation pyramid. So we have 4 levels of geotechnical input on projects, starting from the bronze, silver, gold, up to platinum. So as one moves along the pyramid from bronze towards platinum, your factor of ignorance reduces. So I'm talking about factor of ignorance as against factor of safety. Reliability of design is enhanced. There is a reduction in the foundation cost and construction time, and you minimize the possibility of failure. So let us look at the risks and costs involved as you go from the bronze to the platinum level of investigation. So the bronze level would be very minimal investigations, whereas the gold level is a very comprehensive site-specific investigation, including in situ tests, maybe load tests, use of advanced softwares, and such modern technologies. The cost obviously of the investigation goes up, could go up as much as 5 times, but obviously the level of safety will increase, and the design is optimal, and the saving here is on the foundation cost. Whereas the investigation cost increases, the foundation cost goes down. So you have a reduction in the factor of ignorance. You are better off if you were to do your load tests on site, and there could be a substantial saving in the foundation cost. So let's move towards gold and platinum levels. Avoid bronze level investigations. The geotechnical investigation program should be tailor-made for the project site, as per the site conditions, as per the project requirements, And the involvement of the geotechnical consultant should continue right up to the construction stage. On most projects, you have a geotechnical investigation agency drilling a few boreholes, submitting a report, and that's it. And the project team doesn't get back to the consultant unless, of course, there is a failure, so that you can blame the geotechnical consultant for it. So we have to move to advanced testing technologies. If you are still using SPT, go for automatic ship hammer. Hopefully, SPT will become redundant soon. It is increasingly discarded as a preferred choice of penetration testing in Europe and US. Let's discontinue outdated techniques such as trial pits, dynamic cone penetration tests, plate load tests, block vibration tests, etc. And let's upgrade to cone penetration tests, pressure meter, dialectrometer, vane shear tests, seismic methods, geophysical testing, remote sensing, and advanced sampling and laboratory testing. So field instrumentation is the most important part of this. Observational method of design based on field observation and instrumentation should be implemented, and this can optimize your design and make sure that your structure remains safe. Of course, advanced analysis methods and softwares are now very popular. Now, I'll just come to a definition, a few difficult ground conditions, what you see around. So this is soil hillocks in Punjab. This is a hill slope failure. This is a tunnel beneath a site, which we were able to identify luckily before the construction could start, and this averted a major disaster. And you must be familiar with the damage that occurred during the Bhuj earthquake. The liquefaction caused the collapse of many buildings in Gujarat. The Leaning Tower of Pisa is, of course, the most classical case of differential settlement. So now, with this background, I will now present three case studies. The first one is soft clays in Kerala. Second is gravel boulder deposits in the foothills of the Himalayas. And the third is the Artesian conditions in the Terai region in Nepal. So the first case study I will talk about is soft clays in coastal Kerala. So this is the geotechnical investigation which we had done for the Kochi Metro. So this is a section of the Kochi Metro, the Ernakulam junction to Vaitala. This section is geotechnically very, very challenging. It passes through area of soft, under-consolidated clay. Sands at shallow depth are prone to liquefaction during earthquake. The initial investigation by the owner, based on limited data, yielded conservative and inconclusive pile capacities. 4 piers along the alignment near the railway station were investigated in detail. So this is a layout of the area. So these are the 4 piers over a 220-meter stretch. So this is pier 750, 751, 751B, and 752. So the scope was 2 boreholes at each pier to 75-meter depth. Field vane shear was conducted in the soft clay, and static cone penetration tests were conducted at the each pier location. So this shows the boreholes in progress, and that is the vane shear test in progress. The static cone penetration test, because the ground reaction was we could not get in the soft clay, so we had to add dead load to get the reaction. The sectional profile along the alignment, you can see the top sand layer here, and then followed by clay layer, and then we got this peat layer in between, and of course there was a hard clay layer again. So there was substantial variation from pier to pier over a distance of 50 to 75 meters. Groundwater almost at ground surface, and the loose sand between from the ground level to about 5 to 11 meter depth. Some of it was liquefiable, even though that area is in zone 3. So what you get is below that soft to firm clay, a high moisture content close to the liquid limit, under consolidated, that is OCR is less than 1, SPT values 1 to 5, cone tip resistances are very low, and low shear strength. So these were the field vane shear strength. On the lower end, we got 0.25 kg per centimeter square. So below this, you had hard clay to 60 to 65 meter depth. Here you got good SPT values and refusal below 54 meter depth, high cone tip resistance. Then you below that there was the organic peat to about 75 meter depth. It was also hard with high SPT values but low density, but high shear strength. Below which we got again clay. So these are typical the two boreholes and the cone penetration profile, and the undrained strength interpreted from various tests, lab as well as the SPT and cone plotted here. So this is for PS 750 and similar plot for 751. You can see here the low SPT values as low as 2 and 3 and 751B and 752. So this is a design profile, typical design profile for PS 751, which we developed. The top 3 meters of fill, and then you had this sand layer which was liquefiable. So the negative skin friction in this layer between 5 and 24 meter depth. And of course, in the analysis, we ignored the skin friction in the liquefiable sand. So here, negative skin friction. This is the computed pile capacities for a 1500 mm diameter pile. So you can see here that where you had these piles in sand, for capacity of around 600 tons, you needed about 53 to 55 meter long piles, whereas 751B and 752, where the sand layer was missing, the pile tip had to be resting in clay, and to get 600 plus tons capacity, we required nearly 70 meter piles. So with this, I go to the second case study, gravel boulder deposits in the foothills of the Himalayas. So this is the Bain Bridge in the Jammu Pathankot section of NH8. So this is the investigation program for the bridge. So the bridge details that it's a 259 meter long bridge with 10 spans, 2 abutments and 9 piers. So the span was about 25.9 meters, and the average bed level is 368, and the maximum cover level is 366. Bed protection was planned to limit the possibility of cover. This is a view of the existing bridge. You can see here, so the new bridge is coming up parallel to this. So you can see the boulders on the in the riverbed here. So this was the condition at the ground surface, only the boulders. So there is an infilling of soil in between the pebbles and the gravel. So I'm sure you're aware, boreholes in gravel boulder strata is a driller's nightmare and a big challenge to the geotechnical engineer. In strata with large boulders, more than 150-200 mm, if the percentage of boulders exceeds 40 to 50%, the progress of drilling could be very slow, and it could result in damage to the drilling bits. Collecting representative samples could be very difficult. Standard methods given in the IS codes, such as shell and rotary drilling, may be extremely slow, or they may even fail. Engineers have tried various methods or combination of methods with varying degrees of success at different sites. So the popularly used methods here is the percussion drilling, which is a mechanized shell and auger using a chisel to pulverize the large boulders. It is slow, particularly if the boulder size is hard, some 2 or 4 meters, grout it, wait for 24 hours, and then continue again. Large diameter boreholes are using piling equipment, 400, 500 mm diameter piles equipment. The problem here is cleaning the hole effectively is difficult, and because of the refusal, you don't get very good representative SPTs, of course, and the high cost of the piling equipment. The DTH ODEX drilling, or down the hole vibratory hammer, with simultaneous advancement of casing, popularly used for tube well drilling. This has also been tried out. Air flushing is used to clean the hole. The progress is fast, but the boulders are pulverized, so representative sample is not obtained. Let's see what the IS code says. It says that the performance of boulder deposits under load is a matter of intelligent guess. It depends on the size of and quantity of the gravel boulders, and also on the nature of the and the amount of the filler material in between the boulders. So it is left to the ingenuity of the geotechnical engineer to develop a suitable scheme which can give you a realistic estimate of the safe bearing pressure within a reasonable budget. Basically, here the IS code gives up and does not give you much support here. So in addition to the drilling, various other methods have been suggested by the IS code. These are the boulder block shear test, or the concrete boulder shear test, where you have a concrete block pushed horizontally over the boulder, so you can get like a large scale direct shear test. So the load tests on large size footings or plates. You need to have plate size minimum 5 to 10 times the size of the largest boulder. Geophysical tests are, of course, very popular. So let's see the behavior of boulder deposits under load, where the boulder or gravel is the predominant material, and the filler material exists in the interstices of the boulder. The behavior will depend upon the state of packing of the boulders, the nature and size of the boulders, and of course the gradation. If the quantum of filler material is less, the load carrying capacity is high, the compressibility is low. So you do a plate load test, you get very small displacement. On the other hand, if there is substantial filler material in the interstices of the boulder and gravel, there is an initial stage of high compression followed by a low compression stage when the load carrying capacity is high, and it is the load transfer is through the boulders. After the initial rapid settlement, it decreases considerably, and the boulder take over the load carrying function. So that would be the plate load test behavior here in a later stage. So let us see what is the investigation method we adopted here. It's a combination of boreholes and geophysical tests, as well as load tests. Were used for assessing the stratigraphy and the foundation behavior. Judicious selection of the testing methods can yield substantial savings. So what we did was a combination of the DTH and percussion methods. The DTH was used to progress the hole with simultaneous advancement of casing. The percussion with chiseling was done to obtain representative samples and to conduct SPT. Supplement this with electrical resistivity test and footing load test. Footing load test was conducted on a 2.5 by 2.5 meter size footing to assess the load settlement behavior and the safe bearing capacity. This is a geotechnical investigation using DTH and percussion. You can see this DTH rig here and the percussion drilling rig on the other side. So the DTH drilling, you can see the drilling being done here, and the percussion drilling with the baler being lowered here for doing the SPT. Typical borehole data, you can see here in the foothills of the Himalayas, you have this top alluvium of boulders, and then there is a clay layer in between, and then below that again you get boulders. Of course, you get refusal in the boulder because the is bouncing off the boulders. The next step was the geophysical test. The electrical resistivity test was done. So saving can be substantial if you can interpret the resistivity data effectively. Used in conjunction with the borehole, you can make a good assessment of the stratigraphy. So that's the schematic of the resistivity test when a configuration was used. So this is the results of the resistivity test. So we were able to identify these three layers, the top boulders, the clay, and then the boulders again. The footing load test on a 2.5 meter by 2.5 meter size concrete footing. The load settlement curve, you can see that the test up to which it was done, about a little over 6 kg per centimeter square, we have less than 5 mm settlement. So the test results were so ultimate bearing capacities greater than 65 ton per meter square, and the back calculated phi value is 42 degrees. So we interpret the E value as well as the K value, and then the consolidation parameters of the clay stratum was determined from the lab tests. So the design profile for the analysis, and so the foundation design was it was done for 25 ton per square meter, a little conservative, but that was the design which the designer had value that the designer had taken in his analysis. So estimated settlement was about 8 to 10 mm for an 8 to 10 mm size, a meter size foundation is about 24 mm. I now come to the third case study, Artesian conditions in Terai region of the Indo-Nepal border. Artesian hazard is, of course, a localized phenomenon. It results in loss of shear strength or ground subsidence as a result of quick condition or liquefaction. It could result in slope failure in hilly regions. Could be quite dangerous, could cause damage to structures and disruption or loss of life. So Artesian condition is likely when there is a confined granular stratum sandwiched between two cohesive strata. So this is the Artesian phenomenon, where you have the recharge zone here, and when the ground, when there is a recharge, rainfall here, so you can see that these piezometers are, the water is above the ground level. So this would result in a sort of a fountain type of scenario coming above the ground. So this is a big engineering challenge, not just to the geotechnical engineer, but to the structural designer as well as the construction engineer. You can see here when we were doing the geotechnical investigation, the water was overflowing from the casing. So I will now present the case study of river Shivaganga. We had done investigation for 9 bridges along this highway, Kohalpur Mahakali highway. We got artesian at almost all the 9 bridges. But this one is the case of Shivaganga river here. So this bridge, 253-meter long, 8 spans, 2 abutments and 7 piers. We had 25.9-meter long spans. 1 borehole was drilled at each abutment to 40-meter depth, and 1 to 30-meter at each pier, 7 piers, so 7 boreholes for that. And approaches also boreholes were done. So this is a stratigraphy. Here you can see this is the top sand layer and then a clay layer in between here, and this confined sand layer. The numbers you see here are the artesian pressures. In the deep, we got a second artesian layer down here. You as much as 4.3 meters above the ground was the pressure, and a third artesian layer here. Here the head was as much as 11 meters above the ground. So you can see the head being measured. So the standpipe, we saw the water up to 11 meters above the ground. So the total uplift pressure at the artesian level is 33 meters of the depth of the strata plus 11 meters above ground. So we have 44 meters of water pressure. So what we observed was that higher artesian pressures were recorded during rains compared to the dry season, and increased superficial flow in the river appears to increase the underground flow. Same layer recorded varying artesian pressures during different times during the investigation. So the period of investigation is most important, and trying to make an assessment of what could be the maximum artesian pressure is most important for the design. So let's look at what the foundation design concept was used. The foundation depth will depend on the number of the artesian layers and the depth of the layer. Ideally, if you can keep your foundation depth within the clay layer, you are safe if you are to go for piles or wells. But if your well foundation, if your well foundation is in the clay, that would be good. But if you have to keep it in the clay, sand layer, then the design has to be done very carefully. For shallow foundations in the shallow artesian layer, you could have for foundations above the artesian layer and bed protection to avoid quick condition. For deep foundations, safety is critical. The well should penetrate beyond the shallow artesian layers and sufficiently into the underlying artesian layer. Construction should be done during the fair weather conditions to avoid problems in the upper artesian. So go on to the design criteria further. The critical thing is check for bed boiling. That is under maximum scour condition. So under the maximum scour condition, the artesian pressure should not cause a quick condition or displace the soil above it. So the effective overburden pressure has to be greater than 0. So when you have a foundation in the so below the next artesian layer, so there is a soil cushion uh, uh, above that artesian, so that should not puncture through with adequate safety factor. So the soil cushion has to be thick enough to be able to ensure that your foundation is safe. Then is the third criteria, the bearing capacity criteria. At the artesian level, the effective soil resistance has to be greater than the induced pressure from the superimposed load. So in the term QNQ, you will be using the effective overburden pressure after subtracting the influence of the artesian. The basic concept, the details, of course, I'm not going through because of shortage of time. You can go through it in our paper on Shiv Ganga, which was published in ARC in Singapore. I will just show you one picture of a bridge that failed due to artesian, which was very close to Shiv Ganga. So the risks are there, and we have to be very careful about it. So with this, I'd like to conclude this presentation. Geotechnical investigations in difficult ground conditions requires thorough understanding of the site conditions. Thorough knowledge of local conditions is essential for proper assessment and correct interpretation. If the ground condition throws up surprises, the strata condition should be evaluated effectively to work out a proper solution. Let us not be bogged down by the surprise. Let us take it as a challenge and do it. So here you may have to go much beyond the conventional method and IS codes to come up with the right solution. In conjunction with boreholes, in situ tests, load tests, geophysical tests, and other tests can can confirm the continuity of the strata, evaluate the stratigraphy, and determine your relevant design parameters. The testing program should aim at saving on time and cost of investigation while improving the reliability of data. Ingenuity and careful planning, including appropriate tests to evaluate the problem. You have to make the investigation site specific and come up with interesting solutions which can work. Easy solutions. Thank you very much for your very kind attention. I would be happy to take questions. Anything which you would like to ask. Thank you. Thank you very much. It's been a great pleasure, and thanks to IGS Guntur and the students chapter. In fact, the students of Guntur have been doing an excellent job. Daily webinars, and I think after this corona crisis blows over, in the next 1 or 2 years, geotechnical engineers from Guntur will be the leaders in geotechnical engineering practice in the country, with so much input from so many speakers. Thank you very much.
Thank you, sir.